Hi, everyone. Welcome to this week's discussion. As usual, we will first review some of the key concepts covered in this week's lecture, and then we will move on to our projects, and I will answer specific questions you have. Okay, let's get started. This week, we talk about orientations, and first, let's distinguish two key terms in our discussion. These two terms, orientation and rotation, they are sometimes they are used exchangeably in our daily life, but they are like fundamentally different concepts in our study. So orientation is the instantaneous property, status, configuration, or whatever you call it of an object. So it's something internal to an object. So it changes over time, but it's something of an object. And we can think of it of a rotational equivalent of position. On the other hand, rotation is the change of orientation. So it's a change of some state being applied to an object. And we can think of this as rotational equivalent of displacement or translation, which is the change of position. And now we talked about some of the problem or the difficulty of representing orientation and why we don't have a universal way to represent orientation like we do for position. For position, we have Cartesian coordinate, and almost everyone uses this to represent position because if an x, y, z in 3D can easily, precisely, and uniquely describe the position of an object. In particular, uniqueness is the key property because when we write something like 3, 4, 5 in a coordinate position, we wanted to uniquely determine position in our Cartesian coordinate. We don't want one XYZ could represent more than one positions. And of course, we want something similar or equivalent to this for orientation. But unfortunately, there isn't one as good that has all these like advantages. So let's look at some popular candidates. We have Euler's angle, we have rotation or rotational vectors, which is an axis angle representation. We have the traditional matrix, and in 3D it's 3 by 3, and we have quaternions, and maybe we have even fancier stuff, but we are not going to cover them in the lecture or in our discussion. So let's look at them one by one. First, we have Euler's angle, and by the way, it's called Euler, but not Euler. So make sure you pronounce the correct thing. Euler's angle can represent an orientation with three numbers, and these three numbers are the angles around each principal axis, x, y, z, in 3D. And note that it's not always or necessarily x, y, z in this order. If we assume we limit ourselves to three rotations without successive rotation about the same axis, because otherwise you can just combine these two and add their angles together to get a two-step rotation. So if we limit ourselves to three rotations, we could use any of the following 12 sequences, but note that there are still a lot. So most of the time, people just pick X, Y, Z. And first, let's look at some disadvantages or problems with Euler's angle. So the biggest issue is that the order of those three angles does matter. So unlike Cartesian coordinates that represent a position, like if you move up 5 units, move rightward 4 units, and move forward 3 units, you can combine these three, you can reorder or permute these three steps in any orders, and you always end up to that unique same position in 3D. There is no ambiguity. But this isn't true for orientation, so I'm not going to lead this experiment, but you guys all have my slides. Maybe you can do it now or after our discussion. You can do this little experiment with your phone, and you can convince yourself, believe it or not, intuitively or not, different orders of rotations can result in different final orientations. So that means the order of rotations does matter. And somehow equivalently, this also means that two different orders angle representations could mean the same orientation. So we lost the uniqueness property we want. So that's one big problem with Euler's angle. And another one is a kind of subtle but also critical one. It's called gimbal lock. Gimbal lock. This results when two axes effectively line up, resulting in a temporary loss of a degree of freedom. So honestly, I couldn't understand this sentence anytime after I've read this like 10 or 20 times. So I couldn't understand when I took the course, and I still couldn't understand it now. So I bring you a GIF, a small video. So you can see that those two little stuff, if you connect them together, like here, so scallop-like stuff, if you connect them together, these are effectively the axis, an invisible axis. And we can see that the purple and blue axis, they line up in this gimbal lock, and the green axis goes vertically. And when two axes line up, effectively you drop from 3D to 2D, and you can only rotate in this 2D subspace, and that means you lose a degree of freedom. So you have less freedom of choice to rotate your object. So there is some problem. So that's what gimbal lock means. And now let's look at an advantage of Euler's angle. An orientation can be represented by a single 3x3 matrix. That is good because we are familiar with matrix. And how to represent it? Like on the left, this is the Euler's angle representation. The small r means a real number, an angle. So Rx is the rotational angle around the x-axis. And we can represent as three rotational matrix around each axis that you are familiar with. C means cosine and S means sine. And pay attention to the order of the matrix multiplication. So things on the right will be multiplied with our orientation or the position first. So it's rotated first. So in this example, we rotated first around the x-axis, the y, and finally z. So we put Rx, the rotational matrix of x, on the right-hand side. And also, now we introduce the second stuff. It's called rotational vector. And to bring up this, we first need to introduce Euler's theorem. Well, part of the Euler theorem says any two orientations can be related by a single rotation about some axis. And naturally, we can represent an orientation with one axis and one angle. That's four numbers, because an axis is three numbers, a vector, a vec3. So in the past, we used three numbers, that's three angles for each principal axis. Now we use a non-trivial, some arbitrary axis and only one number to represent that. And you can notice that, like, at first, it seems like we need four numbers, like three numbers for a vec3 axis and one additional number for an angle. But note that the magnitude of a vector representing an axis carries no information. So for an axis, for some axis, like 110 is exactly the same as 220 or 330. So that means the magnitude carries no information, and we can use its magnitude to represent the angle, and then we can reduce this kind of representation to three numbers also. So for example, if we want to rotate around 3, 4, 12, this axis by pi over 4, so that's 45 degrees, we can represent them as pi over 4 times this vector. Note that I picked this example because the sum of square of 3, 4, and 12 is the square of 13. So essentially, this thing is the normalized vector or normalized axis of the vector representation. And also, we can turn a rotation vector into a matrix. And I'm not going to read aloud this conversion. It's just a formula for each entry. You just copy it when you're writing your code if you once need to write this. So this is a matrix as a rotation theta degree around an arbitrary unit axis A. So note that it should be a unit axis. And we move on to the third class of representation, which is matrix, our old friend, the classical one. So we don't need to introduce it further. We just need to like compare its advantages and disadvantages, the pros and cons. So for pros, matrix can incorporate shears. Shears is something that's kind of harder to understand. So mathematically, it's adding something from the other axis to your current axis. But I prefer not to like understanding in this way. Instead, I give myself a geometry example. So shear simply means that you can turn a square into a parallelogram. So you somehow distort your perfect square. So it's not, so it doesn't have, or it loses its perpendicular angle, the right angle. And on the other hand, it can also, I mean, not on the other hand, also it can also incorporate scales. This is easy to understand. Scale is something that turns a square into a rectangle. So matrix can incorporate, or precisely, rotational matrix can incorporate shears and scales in the same 3x3 matrix, so without any additional storage. And for those of you who are familiar or have some idea about computer vision, they like to incorporate also the translation or the change of position and put them all together in a 4x4 matrix. Or I guess in your CSE 167, you talked about homogeneous coordinates, so that's also something related. So it essentially means we can use the 4x4 matrix instead of 3x3 to also include the translation, the change of position, in addition to rotation. And what about the cons? First, it has numerical issues, but we are not going to dive deep into this. It's not a math class, but it's obvious that it has storage issues. We already covered two representations, which are Euler's angle and rotational vectors. They only require 3 numbers, but now with a 3x3 matrix, you need 9 numbers. And also there is a user interaction issue. It's not intuitive. So for Euler's angle, if I say I want to rotate less along y-axis, so what do you do? So assuming you have an XYZ order of representation, you just decrease the second number a little bit and give it back to me. So is that okay? But what if you have a matrix representation and I'm asking the same thing? You don't know how to do it. And also we have interpolation issues. Like, I want to dive into this a little bit. When are we going to use interpolation? So imagine in your animation, you want someone in the animation to rotate its head leftward 90 degrees, but his body is stand still, so his wrist is still facing forward. So it's this man or woman only rotate its neck to the left. So think about what happened to the body, which is between the upper body, between the wrist and the neck. You need to interpolate their position by interpolating the rotational angle. So like I said, the neck is rotated leftward 90 degrees, but the wrist is standing still, so its rotation is 0 degrees. So you can think that in the middle point, like the chest of between your wrist and your neck, it should effectively rotate like 45 degrees. So that means that 0.5, or the midpoint interpolation between 2 points. And for those positions or particles or whatever you call it, closer to the wrist, it should be rotated less because the wrist is standing still with 0 rotation. For the part above your chest, it should rotate more because it's closer to the neck, which rotates 90 degrees. And finally, we talk about quaternions. We talked about it in greater details. So first is an innovative and powerful way to represent orientations, and it's arguably better than rotational vector. We will look at it in the pros and cons comparison page. So first, the basic form of a quaternion is just 4 numbers. If you don't want to like mess up with the underlying mathematical property or magic, you can just think of it as 4 real numbers. As long as you know the those very few computation rules, you are good to go. So so those are 4 real numbers, and sometimes we want to represent in short with S and V, which S is the first number, Q0, and V is the last 3 numbers, Q1, Q2, Q3, which is VEX3. And because it's called quaternion, we pick its first letter, and most of the time we represent with a Q. So there are some basic rules of the imaginary plane spanned by the last three numbers, the V, the vector. And also this specify how should we combine terms after a quaternion multiplication. So in the imaginary plane, the I squared, J squared, and K squared, which they are also -1. And also that holds for IJK. Why? Because we can look at the last three properties. So I is equal to JK, and if we reverse the order of any two bases, we put a negative sign. So we can see here, if we make the last JK into an I, we have I times I, which is also -1. And now we have like, how do we multiply two quaternions? So say we have two quaternions Q and Q prime, which are SV and S prime V prime respectively. So that's their representation. So notice that this comma separates the S part, the real number part, and the V part, the vector part. And that's how do we convert on the right, this is how we convert a quaternion to a matrix. If you look back to the lecture slides, we'll find that from quaternion to matrix is pretty straightforward like this, but from matrix back to quaternions involves some like complex computations we're not going to cover here, but Professor Rodenberg has provided, I guess it's a code or pseudocode from someone that does this job. So if you need that, remember to look back to the lecture slides. So why is quaternion important? We just covered its basic properties and operations. So let's introduce its relationship with rotation. A rotation by an angle theta around axis A, again, is represented by this quaternion. So the first real number is cosine half theta, and the vector after it is the axis times sine half theta. But note that there is redundancy. SV and -S, -V represent the same rotation. And we can see that rotating around axis A by 30 degrees is equal to rotating around axis -A. So it's the same line, but pointing towards the opposite direction by a negative same degree, 30 degree. And like computationally or mathematically, if you look back to this formula, remember that cosine negative theta is equal to cosine theta. So the number, the S part doesn't change. And for the V part, the vector part, if we have -A and sine theta is equal to negative sine negative theta, then those two negative signs cancel each other. So we have the same representation or the same orientation by negating both S and V. So there is redundancy. So again, there is no uniqueness. But that appears not to be a really big problem. And I'll first introduce its advantage. We can composite or combine. I prefer not to call it adding or add two rotations because, as you can see, it's effectively multiplying their representing quaternions. So I prefer not to call them add two rotations together. So we composite or combine two rotations by multiplying their quaternions together. And that is why it's better than rotational vector, because quaternions can answer what is a rotation by combining these two rotations, while rotational vector cannot. So remember that rotational vectors have arbitrary axes. So if you have two rotations, you're likely to have two completely different arbitrary axes, and you have no idea how to represent them. And here, we again talk about interpolation. I will not repeat what is interpolation in computer animation, but in mathematics, recall we are kind of familiar with linear interpolation. It's like picking some weighted average in the middle of 2 points or 2 position or 2 something. So in programming, we usually call this function LIRP, linear interpolation. So this is a function. But to interpolate two unit length quaternions, these two quaternions lie on the 3D hypersphere in 4D. So it's you can think of like a higher dimension 2D sphere in 3D. Of course, we can all imagine a sphere, a unit sphere in 3D. So this is something equivalent in the 4D space. We have a 3D hypersphere, 3D unit hypersphere lying in 4D, and all those unit quaternions lies on this hypersphere. What should we do when we want to interpolate them? We need spherical interpolation. So you can think of it as interpolating 2 points on a sphere, and the result is not something in the segment connecting them. It's the arc connecting them on the sphere. So SLIRP, spherical linear, it's not linear, so it's spherical interpolation, has the formula like this, and note that the theta is also something we need to compute. It's the dot product. It's the arc cosine, or cosine -1 of the dot product between the two quantity we want to interpolate, AB. And finally, let's go back to the pros and cons of quaternions. So comparing with Euler's angle, it has no gimbal lock issue. It will not lose a degree of freedom and like something lock itself to specific plane. And it has faster multiplication and smaller storage compared to matrix representation. So some of you are familiar with time complexity of matrix multiplication. If in a naive way, is 3 by not 3 by 3, is n cube complexity. Well, for quaternion multiplication is faster, and also quaternion only needs 4 numbers instead of 9 to represent an orientation. And like we said, it can combine rotations easily comparing with rotational vector. But still, we suffered from the 2-to-1 duplication, so we lose the uniqueness property. The quaternion doesn't have the uniqueness property. Yeah.